Andrea did his PhD studies at the University of Chicago and a postdoc at the University of Turin, and now he's a professor at the University of Torino. And his activity field of research is mainly on the astrophysics of the study of jets, especially from active galactic nuclei, pulsar wind nebulae, and stellar jets. And he's the developer of the PLUTO Code, which is very famous. So many thanks, Andrea, to come here to give us the talk. Please go ahead.
Okay, well, thank you, Fabio. All right, so the talk today will be on numerical simulation of astrophysical plasmas using also, I should have written also particle-gas-hybrid schemes, okay? This is a list of the people that contributed to the development of the code through the years. Some of them are still active, some other are not so active, but anyway, I wanted to mention everybody who in the last 10 years made a contribution to the code. Let me just do a brief synopsis of what the talk is going to be all about. So the first part, I would like to introduce astrophysical plasmas and the theoretical description behind them. During the second part, we will talk about the computational approach that is mainly used in the fluid approximation. Then I will briefly mention the PLUTO Code, what it can do, and also mention the gas-particle hybrid methods. Then I will cover 3 different species of particles which are included in the code, which really serves for different purposes. Dust grains for proto-planetary disk. Then we have the hybrid MHD-PIC model that is particularly useful to model particle acceleration. And also a last one, which is a non-thermal Lagrangian macroparticles approach, which is very useful for huge or very, very large scales. Okay, but let's begin. Okay, astrophysical plasmas. I want to review some of the concepts because I wasn't sure how many of you are familiar with the description of a plasma. So I would like to highlight the differences at different scales. And indeed, the major challenge in astrophysics when modeling plasma comes from scale separation, because when we are describing astrophysical phenomena, they involve processes which are operating at very different spatial and temporal scales, and those also require complex interaction between plasmas and radiations. Okay. Now, the current computational modeling that we have, but also the theoretical model that we have, it's very fragmented under different views, depending on whether you are applying them to the small scale, intermediate scale, or large scale. So, for example, on one side, at the very high frequency, so small temporal scales, and also small spatial scales, you have the kinetic or PIC particle in cell approach. And this is the left hand of this diagram. While as you increase the time and space, then you gradually move from this description to the fluid description, which is completely different. Now, there is a huge gap, as you can see clearly from the diagram, stretching from particle in cell from MHD. There are several order of magnitudes. And this is what is making plasma description challenging. Now, just to give you an idea, a kinetic description is applicable when you study small-scale kinetic effect. Kinetic means that you are describing both at the same time the motion of the particles like ions and electrons, okay? Now, when you try to model a plasma in this way, the best you can get is modeling length that are approximately a few thousand kilometers and time scale of the order of 100 seconds, but no more than that. Now, for a typical astrophysical application, these scales are really much more smaller. They are several order of magnitude smaller than the actual system size. But that's the only way to have a really consistent model of a plasma. Now, if you are not satisfied with this, because the scales you want to model are much larger, then you need to model to move on to either hybrid kinetic or fluid models. Now, kinetic models are kind of in between, because the electrons electrons are modeled as a fluid, as a neutralizing fluid, and ions are solved using a particle approach. Now, this approach must resolve just the ion inertial length, which is larger than the electron. So then at this point, you can move to distances which are approximately the distance between the Earth and the Sun, okay? 1 astronomical unit on a time scale of a few hours. And if you look at the diagram on the right, then we are moving gradually from the top, which represents small scale, high frequency, to the bottom, which represents large scales and low frequencies. Okay. Now, if you keep moving down, then you encounter the two fluid approximation, one fluid, and then MHD, and then you enter completely in the fluid approach, okay, which is the best one if you want to resolve very large scales. So we're talking from light years to kiloparsec, and temporal scales which go well beyond the day, and they typically stand up to several hundred or thousand years. Of course, you may ask naively, why don't we model a plasma by solving each particle equation? Okay, because this would be actually the most consistent formulation, but that's a nonsense, because you will end up having too many degrees of freedom in describing this, okay? But this will be, of course, the best approach. Of course, you will have too many particles and a very large amount of information that you will need to process out. That's why the classical plasma description is never actually used unless you're using a test particle approach, in which case the number of particles is considerably reduced, okay? In any case, as you can see, in a plasma, there are two components already visible from here: the particles on one side, okay, and the electromagnetic fields on the other. Now, particles and fields will interact mutually in the sense that particles will create fields and fields will affect particle motion. And this is like a loop circling. Now, if you really want to get to something which is doable and usable, then you need to use a kinetic description at least. I mean, you solve Blasov equation, for example, if you are dealing with a collisionless plasma. Now, this is Blasov equation. It's essentially a continuity equation in phase space for the distribution function, okay? F, therefore, gives the number density per unit element in phase space. Particle in cell exploit exactly this approach, and the particle in cell or PIC method can be considered as a finite element discretization of that equation or the Blasov equation. Then you can think of the distribution function as given by the superposition of several elements called superparticles, okay, where each element represents a large number of physical particles that are near each other in phase space. Again, this approach is very consistent, but has to resolve the plasma electron skin depth, which is about 10 to the 5 centimeters. So we're talking about kilometer size region. Now, the fluid approach is introduced whenever you want to move on to larger scales. And also for another reason, the distribution function normally is not a measurable quantity, okay? It is not something you can measure. Also, the Blasov equation presents a lot of difficulties since in essence you have, it's a 6-dimensional space involving 3 coordinates in space, but also 3 coordinates in velocity. Therefore, people go to the fluid approach by giving up, in a sense, or let's say better, averaging on the velocity. Now, if you take the distribution function and you take the average in velocity by considering velocity as an independent coordinate in phase space, then we remove the dependence of velocity and we end up having just quantities which depend on space and time, but no more velocity. Then we can define the number density, okay? Then the fluid velocity, which is, as you can see, the average weighted on the distribution function, and likewise also the energy, the kinetic energy. This is the fluid approach. Now, the fluid approach makes sense whenever you can consider the system as a continuous medium, okay? And you can consider the dynamics of a small volume of the fluid. Of course, the mean free path of the individual particle must be much smaller than the actual scale length. And the fluid element is actually infinitesimal, but not so infinitesimal. Okay, it's small, but not infinitesimal. It is considered infinitesimal for mathematical purposes, but honestly, if you take a volume of fluid, that should be even still large enough to contain a statistically meaningful number of particles, okay? Because then you want to apply statistical analysis as well whenever you want to say, okay, my distribution is, say, Maxwellian or whatever, okay? Now, at this point, if you make this assumption, the fluid equation involves only the moments, that is number, density, velocity, and energy, but not anymore the distribution function star, okay? That is, this sentence is actually not completely true in a sense, but it will take me too much time to explain why, but I'm willing to take questions if you want, okay? Let's say just that in the fluid equation, the distribution function does not appear anymore, but actually its influence is felt in another way. For example, if you consider an ideal or a viscous fluid, okay, that's when the distribution function makes a difference. Now, the moment equation that you recover by doing this average will lead you to an infinite chain of equations which must be closed in order to be solved, and this is the closure problem. However, people adopt some closure, and normally equations can be solved right away. Okay, for example, in the two-fluid description, you average the distribution function of the ion on one side, that's the equation with the predix I, and the electrons on the other, E. Okay, now the two-fluid description is valid again when the mean free path of the particles is less than L. And why do we need to represent two species? Well, because maybe the two-fluid equations is applicable to those systems where electron and ions or protons have not thermalized yet. So we have two populations living on different temperatures and different properties. That's where the two-fluid equations are useful. Now we get two continuity equations for the N, two momentum equation, two energy equation, and still the Maxwell's equation. I didn't write the coupling term because, of course, Maxwell equations are coupled by the current density, okay, with the plasma. And the ion and the proton are coupled between them by this friction term. REI is essentially a collision term, okay, or let's say an interaction term between the two species. Now, the two-fluid equations are approximately here in our diagram, which moves from small scale to large scales. However, there is still a challenge because one huge problem is that the ratio of the masses between proton and electrons is extremely large. And so that will give disparities in the choice of the temporal or the time step. Suppose you are making a simulation, okay? You have electrons are moving really fast and protons really small. They are very low, so slow. At this point, you need to take many steps for the electrons in order for the ions to do something, okay? And this is the challenge. Now, you can still simplify the equation by putting them together, okay? And averaging down ions and electrons equation. At this point, you get another model, which is called the one-fluid model, which is a set of 15 equations, 21 unknowns, which can be closed by assuming some formulation for pi and q, which represent respectively the viscous stress tensor and the thermal conduction vector. Okay, so this system of equation is quite complicated, especially because one law, which is horrible, let's say, actually we can say it's really an horrible law. It's called the generalized Ohm law, which it is the fifth one, which you see here. Now, this law is really difficult to be solved because as long as you keep the physics of electrons, you will always have problem with the time step, okay? Because the electrons move very fast and protons are very slow, essentially. This is the idea. That's why people don't usually solve the one-fluid model unless it's strictly necessary, but they really go to MHD. which is the simplest model to treat an astrophysical plasma at large scale. Now, MHD, which is magnetohydrodynamics, treats the plasma like a conducting fluid and assign macroscopic parameter to describe a particle-like interaction. If you decide to embrace MHD, then you are assuming low frequency. That is, any frequency in your system is much smaller than the plasma frequency, the cyclotron frequency, and the collision frequencies. Then you also assume large scale. Anything in MHD is larger than the scheme depth or the gyro radius, or the mean free path. Then we completely ignore electron mass and finite Larmor radius effect, which is the same as saying, okay, electron physics is not present in MHD. Then you need to assume that the plasma is strongly collisional, or at least that you have a local thermodynamic equilibrium. This condition on collision can actually be relaxed, okay, but this also requires me some time to explain why. But let's say there are formulations of MHD that are also valid in the collisionless limit. The other thing is that the fields and the fluid will fluctuate on the same time and length scale. This condition can be also relaxed if you move to relativistic MHD, where actually this condition cannot be fulfilled in the full way. Of course, there is no charge separation, no electric force or displacement current. These are finally the equation of MHD. Now, if you look at them, the way I wrote here, they actually are quite simple, because you can think of them as the Euler equation of ideal fluid on the left-hand side, plus some extra term. We have J cross B, which is the Lorentz force acting on the fluid. J is the current density. And then we have an extra equation, which is the Faraday law, okay? The law of induction. Now, of course, these are the equation. There is a total of 1, 2, 3, 4, 5, 6, 7, 8 equations, 8 equations to be evolved in time. But then there are some additional relation, because you want to describe. So, for example, Ampere law is not used in MHD. Well, it's not used as an evolutionary equation. It's used as a relation between current and the curl of B. Then you have Ohm's law, which essentially states that the electric field is zero in MHD in the rest frame. It appears an electric field just because the fluid is moving as a Lorentz transformation. But honestly, the MHD is zero field in their proper frame. It's divergence free, of course, and you need to assume an EOS, a closure, an equation of state that relates the internal energy to density and pressure. Now, this is the form that we understand the best, but that's not the form that is actually being solved by the code for a reason.
Andrea, sorry.
Yes.
Quick question. So when there's non-ideal, where do the extra terms appear?
Many, yes. Okay, when you are non-ideal, you will have at least 3 different terms appearing. It's too bad I didn't put my, let me see if I have a slide. No. Okay, let me describe which terms are appearing. First of all, you will have viscosity. Viscosity will enter on the right-hand side of the momentum equation, okay? And viscosity describes a microscopical process by which momentum is transferred between different portions of fluids having different velocities. That will affect, therefore, the momentum equation, but also the internal energy equation, because then you violate a second law of thermodynamics. Entropy is not conserved along a streamline, as in an ideal fluid. So you will need to add the work done by the viscous tensor here.
Okay.
Then you have a second non-ideal process, which is thermal conduction. Thermal conduction is a microscopical process by which the random motion of particles is essentially moving from one region to the flow to another, typically from hot flow to cold flow, even if the fluid is at rest. That term is another, that depends on the temperature gradient, and it is an additional term you want to add to the right-hand side of the energy equation, only the energy equation.
Okay.
Then there is a third term, which comes essentially from collisions, and that's called resistivity. Resistivity refers to the microscopical process when, because of the friction between ion and electrons, then you start exchanging essentially energy between the two species. And that will modify the electric field as well as one extra term on the energy equation, because you heat up the plasma. Think of a wire conduct where electricity is flowing in, is like Joule's law. Okay, so you are just heating the plasma because of friction, and the plasma will heat essentially. Okay.
Okay.
Now, actually, we do not use that form of the equation, but we use this one instead. This is called the conservation form. The conservation form is better, and it can be obtained from the other one just by simple arithmetic manipulation, okay, using vector identities. This is better because you ensure conservation of mass, momentum, energy, and magnetic flux, okay? Now, MHD, ideal MHD is suitable, I said that already, to describe plasma at large scales, but even when it is not suitable, it is still a good first approximation to much of the physics, even if some of the conditions are not met. That's why people insist on using MHD. It also allows you to draw some intuitive conclusion concerning the plasma behavior without recurring to much more complicated set of equations. And first of all, last, the MHD, ideal MHD equation are hyperbolic conservation law. Do you people know what hyperbolic means?
Not all of us.
No, okay, okay. Hyperbolic, so when you're dealing with partial differential equation, there are essentially three different possibilities. The equation can be hyperbolic, or it can be parabolic, or elliptic. Now, elliptic equations are like a Poisson equation. You give a boundary condition such as mass, and you have to find the potential, the gravitational potential, given the distribution of mass. Okay. Parabolic equations are similar to the heat transport equation. They do not involve wave propagation. And hyperbolic PDEs are the only one which allows information to propagate at a finite speed. So if you have 2 points in space and time, they can feel each other only if a wave starts from point A and reaches point B. Okay, so that's the only way the two can communicate. So hyperbolic has to do with propagation of waves, sound waves, fan waves, light waves, whatever you have in your system, but they are waves. Okay, and we'll actually get into this shortly. Now, let's work out a computational approach to fluids, okay? Now, we prefer to use the conservation law because that form is also suitable for discontinuous waves. So you know that hyperbolic PDEs allows as a solution also discontinuous waves, such as shocks, rotational waves, contact waves, for example, okay? And they are closer to their fundamental integral form, where no differential operator is needed, okay? Take, for example, the Euler equation. Now, you can actually integrate this equation and get down to Gauss law, okay? So you can transform by integrating this one, integrate that in space. Then you replace the divergence under the integral with the flux along the surface, and then you have removed any derivative. Now, when you use a fluid approximation or a fluid discretization, you have two possibilities, a finite difference or a finite volume. Now, in the finite difference, you are stick to the differential form of the equation. And then you replace the divergence with the finite differences approximation to this operator. And then you end up having this, okay? But this is really an approximation to a derivative. In a finite volume, you do not approximate the derivative, because before doing anything at the discrete level, you first integrate the equation, you get this. So what you really do is that you are evolving the volume average of u in time and not the point, okay? So finite difference evolves the point at the center. Finite volume evolves the average along the cell. Indeed, if you integrate in time, and then you get a discrete version which is technically exact, because by integrating this log here, you see, do one more integration time, you end up having this one. Now, the average value of u at the next time level, n is the time level, n plus 1 is the next one, is equal to the old average minus the net flux across the boundary, okay? It's very simple to understand. If you have 50 euros, okay, in your wallet, and somebody gives you 10, but you also spend 10 for lunch, the overall budget is 0 because 10 came in, 10 came out, okay? That's the same thing. Okay, so the evolution of mass, momentum, energy is the net of the incoming, and outcoming flux of the boundary. Note that this F tilde is the integral average in time, and this relation is exact. Beware that this does not mean that you can solve the equation exactly, okay? Because at some point, an approximation will be needed. And actually, the approximation comes exactly while computing the flux, because to compute the time average, you need to know the solution, which you don't. And so you need to make some approximation and compute the flux at some approximate level. And in order to compute this flux, people in finite volume Godunov schemes, they solve the Riemann problem. The Riemann problem is very simple. Then you sit yourself at an interface, then you look at the state on the left, the state on the right, okay? And then you ask, okay, I have two discontinuous states. If I let the discontinuity evolve, what will happen later, after? Well, that's the answer comes from solving the Riemann problem. Okay, this is the Riemann problem at time t0. You have a left state, u can be density, momentum, and energy, okay? But they are different on the left and on the right. Then once you evolve the system at time later than 0, this will break up, giving intermediate states. And these states are separated by these dashed lines. We represent in space-time the propagation of waves. Okay, a single wave with a constant velocity in a space-time diagram will look like a line, an oblique line, similar to the light cones that you study in relativity. Okay, now the Riemann problem that we need to solve will require the evaluation of the flux on the axis at the interface, okay, which is labeled by I plus 1/2, because separating cell I on the left from cell I plus 1 on the right. Now, the concept of solving the Riemann problem brings the concept of upwinding. That is, once you discretize the system, you must choose a direction which takes into account the direction from which waves are propagating. So if waves are propagating to the left, then I can use a backward discretization. If waves are coming from the right, I will use actually a right-handed approximation. Okay, so this is the concept of upwind. You cannot discretize in a central way unless you add a lot of viscosity, but an upwind scheme requires you to evaluate where the information is coming from. And for each different wave, you pick a different discretization. Now, the beauty of these methods is that there is no artificial viscosity that has to be added to stabilize the scheme, because the scheme has intrinsic numerical dissipation. Okay, so you need to add an extra. Now, the problem, of course, is that you need to solve a Riemann problem, which usually a complicated task, requires the simultaneous solution of a set of nonlinear equations. That's why people usually don't use exact solution, but prefer instead approximate methods. And the degree of approximation reflects the ability to capture and spread discontinuities over few or more computational zones. In the plot that you see, in the movie that you see here, you see the solution in time of an MHD problem. Since MHD has essentially in 1D 7 equations, one is redundant because the divergence of B tells us that Bx must be constant, then you have only 7 equations, and therefore you have 7 waves, which is a pair of fast magnetosonic, a pair of slow magnetosonic, a pair of Alfvén waves, and one contact discontinuities in the middle. This is the contact discontinuity, the one separating dark green from light green. And then in the top, you can see actually how the discontinuity evolves, because you form different jumps in density on the left and the Z component of magnetic field. Okay. Any question up to here? Okay, good. Okay, now, in the end, a code like PLUTO or many other like Athena or Ramses or ENS or whatever, I mean, all these finite volume codes are based on a very similar sequence of steps, okay? Essentially, you start from the volume average, and at this point, you need to make a reconstruction whereby from the average inside the cell, the volume average, you need to find the point value of the interface. This is done by using a high order non-oscillatory polynomial U of x. That will give you the blue curves, which will end up being discontinuous at the interface anyway. At this point, between these two discontinuous values, you want to solve a Riemann problem, giving you the wave structure represented schematically by the yellow dotted lines. That will give you the flux. And once you have the flux, you can update your solution using any kind of Runge-Kutta, for example, time-stepping algorithm, okay, by using this form, essentially. Now, let's see in brief what the PLUTO Code is, what it does. I know some of you are already using the code, so let me take a very brief introduction to the code. There is a website, the current version is 4.4. Now, PLUTO is a modular, has been designed as a modular code, it's finite volume, and wants to provide a multi-physics, but also a multi-algorithm framework to solve the equation of plasma dynamics in astrophysics. Now, the current support goes towards the compressible Euler-Navier-Stokes equation, Newtonian magneto-hydrodynamics, but also the extension to relativistic. So we have a special relativistic hydro and MHD, and recently also resistive relativistic MHD. And then we have a bunch of different heating or cooling processes. I mean, non-ideal physics like cooling, network, ambipolar diffusion. I keep saying this, but actually it's not in the code already. But we have thermal conduction, resistivity, Hall MHD, and a bunch of other stuff. The computation are possible both on static and block structure adaptive meshes by using the Chombo-Lie. PLUTO scales fairly well. We went up to more than 200,000 processors, achieving very good scaling. That actually was some time back. Now the current version is 4.4, patch 2, I guess. This is probably the last version of the code that will be using CPU, because we are now spending time in rewriting of the code to GPUs, and that's going to take a lot of time. But we already have something nice and with very nice speed up to a factor of 40 or 30-40 in some situations. So, but that will come later, probably 1 year from now. At present, however, PLUTO is still available, of course, to run on CPU, and it has all these different modules, different equation of state that allows you to switch between an isothermal or ideal gas, non-constant gamma, or the Singe gas for relativistic hydro. There is also support for different geometries and Cartesian, cylindrical, spherical, and different source terms, also including, for example, gravity, body force. There is also the shearing box approximation, or the Fargo to deal with differentially rotating systems. And recently we have this particle physics module, which I will concentrate later on, well, actually in a few minutes from now, dealing with Lagrangian particle, dust, and cosmic rays. As I said, the PLUTO is not just modular as far as the physics is concerned, but also the different algorithm. So you can choose between different reconstruction scheme, parabolic solver to solve the parabolic term, Riemann solver, divergence of B control. So there are a lot of options that can be used. Some of them are better than the other. Not all the options can be combined together, okay? But usually the code try to give a warning if we're trying to do something nasty. Well, I guess we can skip on this. It's just a different, this is a summary of all the references for all the modules. There is also, I forgot to mention this, there is a new module on radiation hydrodynamics, which works using the two-moment equation in a relativistic formulation derived by David Mellon-Fuchsman and myself in 2019. Okay, this is our plan to rule over the world. We have, so I see people in Mexico City also here from the map. Good to know that. That was updated almost 1 year ago, so I guess more download occurred. Anyway, now let's go into the fun part of the talk, which is really the fluid particles hybrid scheme. So this is a new feature that has been introduced starting from PLUTO 4.3, and we have enabled 3 kinds of different particles: dust grains to model proto-planetary disk, MHD-PIC to model large-scale particle acceleration, and Lagrangian particle. Now, while the first one has to do with the proto-planetary disk, the latter ones are more suited to high-energy astrophysics. Now, but the concept is very similar for all of them. So imagine to couple a fluid, okay, with a bunch of particles, because they cannot be described in a different way, or we don't want them to be described in a different way. Now, a Goldenow type method then will be the same as before, but with the addition of one flux term, which depends on the particle. So P as imply dependence on the particle, and the source term, which also depends on the particles. Now, the equation of motion for the particle will be very simple: dx over dt equal to the velocity, and then you have Newton's second law of dynamics. The derivative of velocity is equal to the acceleration, but the acceleration can depend not only on neighbor particles, but also on the fluid itself, or electromagnetic field, for example. Now, we want to keep treating the fluid using Goldenow methods, while we want to apply particle in cell techniques to solve for the particles. Okay. Now, at present, scheme are second order accurate, time reversible, because we use the Verlet method for the particle, and there is full parallel I/O. Now, important thing to remember: hybrid methods require fluid quantities to live on a grid, while particles are mesh free. They can move, they can be anywhere on a mesh. Okay. Fluid and particles interact via mutual terms, the red one here. Now, let's try to understand how this works in a simple example, which involves only dust particles. Now, dust grains are relevant in the modeling of proto-planetary disk, okay, because you have sand or pebbles, and the physics is actually quite important to model planetesimals, okay, the very early stage of formation of a planet. Now, the dynamic coupling happens because dust and fluid will feel each other through aerodynamic drag forces, friction, essentially, okay, which will cause the two components to exchange momentum and energy. Now, on the one hand, the fluid will feel the particle via this term, okay, because the fluid will feel particles trying to break down the fluid or accelerating the fluid. At the same time, dust grains will feel the fluid, because while the fluid is moving, we'll encounter, while a dust particle is moving, we'll encounter fluid trying to slow it down. Okay, these are the two coupling terms. It's very simple to understand. Now, how is this coupling obtained? Well, it's obtained using particle in cell techniques, which, very simply stated, require a particle to be represented as a cloud, or better, as a square cloud. So think of a particle as a blue dot, okay, but also think that the particle as a cloud attached to it, and this cloud is a square shape. Now, in the cell ij, only the portion of the square cloud which fits inside that cell will contribute to it. So we have then weight factor, which measure the distance between the particle and the cell. Okay, this weight will be non-zero only when there is a significant overlap between the square and the cell. If the particle is too far away, then the weight will be zero and there will be no interference between the two. But if they are close enough, for example, here the red and the yellow particle will give a larger contribution because they extend much more inside the cell. And then at this point, This is how we fill the particles. And this is actually done also in the other way. So we use this weighting factor for a fluid cell to fill the particles, but we also use the weighting factor for a grid cell to be felt on the particle. So it's mutual, okay? And it's described by this weight factor. So all it matters is just the relative distance between the particle and the center of the cell. That's all, okay? And then with this technique, we can model the contribution by summing over all the particles weighted on the weight function, which is again a function of the relative distance between the two. Now, how do we model particles? Well, particles, we have to be very careful for dust, because dust is a stiff system. Stiff because sometimes your Stokes number, or let's say what we call the stopping time, is so small that the particle will stop in a very small time step, but the numerical method is to capture this behavior. Now, a semi-implicit method is okay, but it will not do the job when the stopping time is smaller than delta t. Okay, and then you will have lots of numerical oscillations. Therefore, we derived an exponential integrator for dust particle, which is really amazing. I don't know if anybody of you knows about this technique, which is, well, it has been out for 20 years, but almost nobody used that consciously, at least. It's a very powerful technique where you can solve the stiffness exactly. And the trick is the following. So suppose you have an equation which is like this one. I don't know if you can see my mouse moving. So dV over dt is equal AV plus G. Now, suppose A is a constant matrix, but is also responsible for stiffness, which is the same as saying that A is a constant coefficient matrix with a large spectral radius. And suppose that G contains everything else, nonlinear. Well, then you can use the variation of constant formula, that is, you multiply by e to the minus at, and then you integrate, and then you get the boxed equation, which is exact. Now, the beauty of this is that the stiff term is captured exactly via an exponential matrix, while the other term, the G, the nonlinear, well, that is not captured exactly, but you can use some approximate technique to evaluate this function. Okay, because it's an integer, you can use Simpson rule or trapezoidal rule. Okay, but the thing is that now stiffness is captured exactly, so you don't care. You can use approximation in the nonlinear term, but the system will be stable because stiffness is captured exactly. Now, for example, you can use the exponential midpoint method, okay, which is second order accurate, time reversible, and it will yield also the correct asymptotic limit when t goes to infinity for any stopping time, which is really amazing. So you don't care about your stopping time anymore. For example, if you have a particle which is decelerating really quick, now you can see here in the plot, you have the analytical solution is given by dashed line. As you can see, it will immediately slow down. Now, the same implicit method will try to capture the behavior by overshooting and undershooting the exact solution many times. By the exponential midpoint in one single time step will actually go to 0 and recover the exact solution afterwards. Okay, and it's also time reversible, which is something you can you can hardly achieve if you use a fully implicit method. Okay, now the exponential method has also one other beauty. It preserves the geometrical properties of the orbit, and it is very suitable for time reversible long time integration. See, now I'm doing tens of orbits, and the energy that you can see here doesn't increase in time, because this is one beauty of symplectic or quasi-symplectic algorithms. The energy is bounded. Of course, you get some precession. If you look closely at the red elliptic orbit, you will see some precession, but the energy is very much well preserved in time. Okay, and the orbit remains closed, which is amazing. So we already did 80 orbits. The energy oscillates around the expected value with no change. And notice that the time step is really large. Then you are asking yourself, what is the result if I use a Runge-Kutta method? That's the answer. If you use a Runge-Kutta method, you cannot even capture one orbit for the most eccentric one, that the particle will just be blown away. So Runge-Kutta methods are not good, okay, to integrate this system unless you take really a huge amount of time steps. In order to use the Runge-Kutta method to resolve an orbit, you need 20, 30, or 40 steps per orbit. This is not true in the case of an exponential symplectic method, okay, which is really superior to Runge-Kutta in this sense. Well, then I don't know if somebody is interested in the streaming instability, but this is typical instability for fluid, for dust fluid, which leads to very heavy concentration of dust, okay, which can then cause fragmentation in the disk and the formation of planetesimal. However, this is not the subject of the talk, so if you are okay and there are no objection, I will actually move on and go actually here to the MHD-PIC model, because I see I already talked enough and there are still many things to say. So let me focus therefore on the magneto-hydrodynamics particle in cell model, which is a hybrid method. Okay. Now, this method is quite useful in handling both, well, let's say that it allows MHD to be extended to smaller scale, because now you can treat the thermal fluid using MHD, but you can treat the non-thermal particles using particles, essentially PIC techniques. So the advantage of this approach is that you avoid resolving the microscopic scales, because you don't need to resolve the skin depth. All you do is caring about the gyro radius. So if the gyro radius is larger than the skin depth, then you are okay. And this is especially true in in high density environments. So MHD-PIC is in between, as the name suggests. We are at the gyro radius scale. Now, how does it work? Now, you can think of MHD-PIC as a three-component plasma, which is made by thermal ions, okay, plus massless electrons treated as fluids, and cosmic ray particles, which is the non-thermal component, treated as particles. So thermal ions, massless electrons, and then cosmic rays, usually ions, that are treated by particles. So you apply charge neutrality to the full system. So ions, electron, cosmic rays. The total current is the sum of this and will still be given by the curl of B. Now, when you derive the equation using the natural MHD formulation, you end up having a system which is very similar to MHD, except for a few additions. So first of all, in the momentum equation, you will have an extra term which accounts for the actual current density of the cosmic rays. And then in the electron equation of motion, you will have an extra term which accounts for the relative motion between the cosmic ray and the gas. This is called the CR cosmic ray Hall term. And it is parameterized by this quantity, which is essentially the ratio between the cosmic ray charge density and the charge density of the electrons. This is a small number. Well, it has to be a small number for the formulation to be valid, because we assume that QCR is much smaller than the other two. QCR is a small population of non-thermal particles, because you want to study the acceleration of these particles. So you consider a small portion of it. Now, when you work out the conservative form, as you can see, you have MHD fluid on the left, cosmic ray particles on the other. Now, you see this term appearing here. Well, this is simply for Newton's third law of dynamics. If the particles are feeling a force, then the fluid must feel the opposite, okay, in order for the total force to be zero and the momentum to be conserved. Now, particles are feeling a force. The force felt by the particle is, of course, given by the Lorentz force. So it's electric field plus the gyration term along magnetic field lines. And conversely, the fluid is feeling the opposite. And of course, this opposite is exerting a work on the fluid. Now you have to consider fluid and particle as a single whole system. The total momentum and the total energy are conserved. But when I say total, I don't intend just the fluid. I intend the fluid plus the cosmic ray particles. The idea is still the same as the dust here. The fluid is treated using conventional Godunov type methods with this addition here, okay? And the particles are treated using a particle cell techniques using Bohr's pusher, for example. Okay, so this is essentially how the numerical scheme evolves. You take a half a step with the fluid, then you do a full step with the particle push by taking advantage of the fact that you have already the solution at the mid-time level, and then a fluid corrector. Okay, and this is how you couple the terms by using this weight factor, okay, in the source term. Particles are updated using a Bohr's pusher, which is a very traditional method of doing that, which is time reversible, and it has good conservation properties in energy and in phase space in general. Now, let's see what kind of physics we can really do with this MHD-PIC approach. Now, one interesting problem is the diffusive shock acceleration. I don't know if you know what that is, but I can explain in short. And the idea is that a particle can be accelerated in proximity of a shock. How? Well, because a particle can be scattered back and forth around the shock by multiple encounters with magnetic irregularities, or let's say scattering centers. This is very important in many astrophysical models. Ones to be cited is, of course, supernova remnants, but also solar flares. Okay. Now, the scattering occurs because the shock is not laminar, but it is turbulent, because the turbulent comes from other kind of instabilities, which are easily triggered from particles themselves. One possibility is the Bell instability. Okay. Now, the interesting thing is that there is an analytical theory that predicts the asymptotic behavior of a population of particles being accelerated at a perpendicular shock. And that theory predicts that the spectrum must go like e to the minus 3 half for a non-relativistic shock. Now, we have done simulation. Okay, so let me explain before we look at the movie. I want to explain what we are looking at. So, top panel is density, middle panel is magnetic field energy, and the last panel represents the energy spectrum of the particle. You will not see the particle in the top above movies just because there will be too many to be plotted, and you will only see the fluid. Now, there is a flow coming from right to left, and there is a wall located to the left. So once the flow hits the wall, it gets reflected, okay, and the reflection causes a shock to advance on the right. At this point, particles are injected at the shock front, okay, and they will start to build up first an instability in the upstream medium, and then by coming back, they will be scattered because turbulence is occurring. So this is essentially what it happens. Okay, let me first stop here. As you see, initially the particles are all concentrated in a very small peak distribution around this value, which is approximately 10 times the energy of the shock. But then as a particle acceleration takes place, then you can see the formation of a tail extending to high energy. The tail moves on, and eventually it will build up a power law, which is very close to the expected values, which is e to the minus 3 half. In the plot, you are seeing e to the minus 1 half because I'm plotting e times f of e. So of course it will scale with one less power. Okay, so this is the asymptotic behavior of our. Now, as you can see, in order to produce this spectra, your scenario must include turbulence, because you need to create scattering center across which particle will be reflected, essentially. So this simulation has approximately 10 million particles, more or less. So you need to build up a statistically relevant sample of particles in order to do this. Now, very interesting if you try to have a look at the most energetic particles in your domain, or one of the most energetic particles. Let me comment on this. So now you can see a red dot, okay, with some trajectory shaded behind. Now, the color of which I choose is that will go all the shades of red. So it will be dark red, meaning low energy, up to orange, medium energy, and up to white, which is actually very energetic. So the color of the particle represents the energy. As you can see, the particle is being scattered, okay, and is changing color gradually, meaning that the energy is increasing. Now, usually this is a stochastic process because the particle gains energy at each encounter, but it always gains, and that's why we call that Fermi first order mechanism. Not, don't worry, we'll come back, okay? Okay, magnetic clamps will provide the scattering center. Now, in the end, this particle will become very energetic, okay? Of course, you need to resolve several gyrations in order to describe this process. Okay, now you can see it's light orange, and it's going to turn almost white. That is. Okay, so this is how Fermi first order mechanism operates at shocks. Okay, there is also another very useful environment where we can use this approach even just with the test particle without including any feedback on the fluid, and that particle acceleration at current sheets. Now, a current sheet is essentially a region where two different, let's say, region of space embedding fields, magnetic field lines with different polarities will reconnect, okay, because of a finite resistivity. That will release the structure that you can see on the top panel. But the nice thing is that in this approach, you can definitely accelerate particle because during this process, you form this huge island, but at the neutral line between them, you can create very large electric fields. And the electric fields are capable of accelerating particle a lot, especially if the electric field is parallel to magnetic field, which is a situation which can be easily generated in non-ideal MHD by using a finite resistivity. Now, usually the spectrum here is a power law in gamma. Gamma is a Lorentz factor, and the law goes like P to the, P is like 4 for C, sigma is the magnetization, and it tends to 2 for very large magnetization. So it becomes harder than in relativistic shocks. Now, the beauty about the current sheet, particle acceleration current sheet is that this is a much more general mechanism than shocks, and it operates almost always, okay? It doesn't require any specific topology of the field like you have in shock. In shocks, you need to assume the field is perpendicular. Sorry, it's parallel, because for perpendicular shock, it doesn't work, okay? So if you try to plot the particles, let's hope that my PowerPoint doesn't crash here because I see, okay, it didn't crash, luckily, okay? So here is what happened, see? Let's go back and take a look at the movie. So now the field will start to reconnect. The particles are represented by these green dots. Now you see the formation of many islands. This is a typical process occurring in reconnection due to an instability called the tearing mode instability, which allows magnetic field lines to quickly break and then rejoin by forming these O and X points. So what you see in dark blue are the O points. As you see, particles are gradually being trapped inside the island, and once they do that, they start gaining energy also because of first order mechanism, because then at this point they start bouncing back and forth in the island, but they are trapped there. And at the end, a significant fraction of the particle will end up being embedded inside this big island, okay? So this is a very interesting piece of physics, and people are trying now, we are trying to compare our result with PIC codes, because the MHD-PIC offers an advantage over traditional test particle approach. Now, finally, let me conclude this talk by mentioning the non-thermal Lagrangian particle. This is even a different approach. Now, the target here is much more than the gyration radius. So you have to use this approach when you are far away from gyration is a microscopic quantities. So this applies very well to AGN jets or also to pulsar wind nebula jet in some circumstances. Now, the idea is very simple. Now, a particle will not be a real particle. Will be instead a collection of particles, let's say electrons, which are sufficiently close in physical space. Now, therefore, a green particle here, a green dot macro particle, is a very large collection of particles that are in the same physical space, but they are very different in energy. So to each particle, we associate a distribution function, which in turn follows a Fokker-Planck-like equation, which is the one boxed here. So for each particle, we have an equation like this. Okay, so if you choose to have 1 million particles, you have 1 million equations like this to be solved, one for each particle. This equation will give the spectral temporal evolution of the particle distribution function. Okay, now particles are moving with the fluid because they are transported at the fluid speed. Okay, but they have attached this particle. Now, the spectral evolution is very complicated because essentially inside you can embed any microphysics that you want as long as you provide the correct recipe, okay? Adiabatic expansion, synchrotron or inverse Compton cooling, shear acceleration, Fermi second order, even shocks, and we are now working on reconnection, okay? Now, at the moment, the standard implementation of the code neglects diffusion and shear acceleration, and it ends up having this simple expression which can be solved analytically by using a exchange of variable and the method of characteristics. But anyway, besides that, this equation does not contain information about shocks, okay? So it doesn't say, okay, well, we have an ensemble of electrons hitting a shock. We want the distribution to be changed instantaneously because the time step is very large, so we can assume asymptotic theory is correct. Now, we want to reincorporate. So the way we do this is not by acting on the equation, but we act on the particle by implementing a shock detection algorithm and then using a subgrid modeling. Essentially, the particle is staying there. So you can see the particle is represented by the white dot here. And its spectrum is given by this oblique blue line in the bottom. Now, as long as the particle doesn't feel anything, there is no feel nothing, the spectrum doesn't really change. But look now. Okay, as you can see, now the shock has hit the particle and the spectrum has been manually changed or automatically changed by using this subgrid recipe, whereby we resect the particle, the macro particle, I should not say the particle, the macro particle, so the ensemble of particles, to the actual Fermi first order distribution for diffusive shock acceleration. Of course, the complicated part of the algorithm is recognizing the shock, but not just the shock, also its velocity and orientation, because the spectral distribution has different value depending on whether the shock is parallel or perpendicular. That will make a difference, a significant difference in the spectrum, in the set, the spectral energy distribution of a macro particle. Okay, so we can look at the movie again. Okay, notice that now the spectrum keeps changing, and these changes are due because of synchrotron cooling. Because it's true that you energize the particle, but it is also true that the particle will lose energy because synchrotron cooling or inverse Compton. Okay, now you can imagine with this kind of approach, you can really move on and do the final next step, which is modeling three-dimensional simulation of, for example, FR2 jet. This is a movie made by Dipanjan Mukherjee, who was in our group and now is still working on these beautiful simulations where you try to interconnect, not to capture not just the dynamic of the jet, but also the spectral properties of the jet, because by injecting the particle, you can sample the physical space with electron, and then you can determine lots, really lots of quantities that can be interconnected with observation. For example, the aging of the particles, the Lorentz factor, the energy at a particular frequency, etc., etc. Of course, all it depends on the recipes that you put in the code, but if they are accurate recipe, then you can hope to get out with some information. For example, one information you can get is the surface brightness of the jet. Okay, then you can filter your losses by computing the amount of energy at 1.4 gigahertz, for example, the power, and then you can trace the power directly. Okay, this is much closer to what we observe than looking at a simple density or pressure map. Okay, you can also study the spectral index, the breaking index, which is essentially the frequency at which your spectral distribution has a sharp cut that goes to zero. And then you can also study the spectral index of the particle. So all this information, where we are now in the process of actually doing more work with this, but of course the potential should be clear by now. With this tool, we can really provide something that we hoped in the past for many years, that is providing the comparison between theory and observation, okay? So between what we simulate and what we see, which is the whole purpose of doing all of this, okay? So this will lead me to the summary, which I leave you to read, and thank you for your attention.
Okay, thank you so much. So, anyone have one question?
I have two questions. Oh, or I don't know if Diego, do you want to go first?
No, you start, Fabio.
Okay, many thanks for the talk. It was very interesting. And so first one about the MHD-PIC. So the particles are not allowed to escape from the computational box because we saw the particle.
No, the particles are allowed to escape. Yes. Well, it depends very much on the problem. If you are looking, I think you were probably curious about this one. Yeah. Well, in this domain, the particle cannot escape from the top and the bottom simply because I use periodic boundary. So once the particle goes above, it re-enters from the bottom. But, however, the particle can escape from the right. If the particle is too energized, then it can leave the region on the right, and then it will never come back. If it hits the final boundary, which is much beyond what you see in the movie, it will leave the domain and not come back anymore. But that's a tunable parameter in the simulation. You can do whatever you want.
But there was a particle coming out from the right, and there was another. So it was a different.
No, it's the same. So, okay. Let me explain. What you see here is not the entire computational domain. It's just one portion.
Oh, okay, I see.
The computational domain is almost 10 times larger.
Oh, it was.
So I know you saw the particle coming out on the right, but it didn't actually reach the end of. See now, it's still in the computational domain, although you don't see it because the movie has been cut.
Okay.
So it will come back, but it will never. It didn't go out. It was still inside.
Okay. The other one about the Lagrangian particles. So how do you recognize the shock? And because
we worked 6 months on this. So we use a combination of the Hoffman-Taylor frame. So first of all, we find the shock is easily recognizable because you can use a criterion which combines the gradient of pressure and the divergence of velocity. But then the particle needs to sample upstream and downstream quantities. Yeah. From these quantities, it is allowed to compute the shock velocity and the direction. Then you project the average magnetic field upstream and downstream onto the direction of the propagation, and then you determine whether the shock is parallel or perpendicular. If the shock is parallel, then you apply standard diffusive shock acceleration. If it is perpendicular, no acceleration. Although now I don't remember exactly, but the paper explains it. I think there is some cutoff at 45 degrees, essentially.
Wow. So it's very complicated. Yeah.
It's very complicated, but I know we tested extensively and it works fairly well. Of course, you know, there are many approximations, but this is the best we came up with.
Okay, thank you. Diego?
Diego, please.
I was speaking with my microphone muted. It's not the last time that's going to happen. So yeah, thank you for your talk, Andrea. I know at least for a few students here that are PLUTO users, it's going to help a lot.
Okay.
So speaking of help for the students, and the questions I have is, from your experience, up to how many CPUs have you seen that PLUTO scales linearly? Like to see if it's better if students use 256, 512, 1,000.
So this is let me rephrase in a different way, because this is a tricky question. You can scale. I can tell you it scales well up to 32 or up to 60,000. The point is, how large is your domain?
Okay.
Okay. So as a rule of thumb, I suggest this: take your problem and use some number of processors. As long as each processor has at least 32 by 32 by 32, the code will scale well.
Okay.
But if you use too many processors, at some point, your single processor will have a domain which is so small that most of the time is spent in communication. Okay? So let me give you an example. If I have a problem with 128 zones in each direction, in X and Y, I can use 4 processors, and then I will have 64 each. Or I can use 4 by 4, I will have 16 processors, then I will have 32. But if I use 1,024 processors for a problem like this, in the end, my single processor will probably have 4 by 4 or 8 by 8 zone. That's not enough.
Okay.
Okay, so try to keep the local size still large enough. At least, I don't know, how can I say this? At least around a few thousand cells, okay, for each processor in total. So 32 by 32 by 32 is a good. 16 cubed is also a good number. But 4 cubed, no. 8 cubed, not so much.
Okay.
Okay. So if your problem, the answer is, the problem is large, you can go up to how many processors you want. We tested up to 200,000.
Well, we don't have that many in Mexico, so don't worry.
No, it's okay. I mean, up to 1,000, it's okay. We scale well. Not so well with the particle, however. I have to tell you this, because load balancing is not accurately taken into account when dealing with the particles. So with the fluid, we scale well. With the particle, we will not scale so well.
Okay. And so another question related with students. So if they have difficulties or questions, what do you recommend to the PLUTO users or to the PLUTO creator?
The PLUTO creator is very busy. Sorry. No, okay. This is what I suggest. Try to post a question on the forum. There are people answering. Sometimes I go there, but very rarely. And try to try to maybe compare with your friends. If you have more experienced friends, ask them. If you think that there is a bug in the code, because it happens, and you are quite sure it's a bug, then you can write to me. But don't waste too many words saying, I have tried this and it doesn't work, because I will not tell you the solution. What you can do instead is to give me the smallest possible problem, such as the bug is reproduced. Then I will take that, will debug it, and then come back to you. Okay? But always give me the smallest possible version of the problem. I don't care. I mean, you can have many elements, but there will be one element which screws your problem up. Well, take that one, make me a short problem that I can run on a single processor. Don't tell me, oh, I get a segmentation fault after 16,000 steps with the 128 processor, because I cannot replicate that easily. So give me something easy to replicate, and then I'll do my best to find the bug. Usually I always do. Okay.
And then something more technical for what we've been doing. So for like relativistic MHD, the Powell or CT or what for the divergence of the magnetic field do you normally use?
Okay, usually if I can, I always go with constraint transport.
Okay.
That's the best way, although constraint transport poses lots of difficulties, okay, because of the staggered representation is really a mess. if you are dealing with complex boundary conditions, then divergence cleaning is also a good alternative, and it works well. It's not inferior to CT. Well, not usually. It's compatible, but don't use Powell. I mean, you can use Powell, of course, just to begin with. Okay, you are in a hurry because your advisor wants to have results by Friday. Today, Thursday, and you want to make the code work. Okay, good. Use Powell just, but then don't use it for a publication.
I'm sure my student is going to be with a heart attack at this moment, because I know with the setup that he has and with the really complex problem, he's only been able to use Powell, and that's like
he can use divergence cleaning. Try divergence cleaning. It's not too much complicated than Powell, actually.
Okay.
Okay.
So if you're like the referee and you see that he used Powell, would you say, no?
If I am a referee and I see a paper published with Powell, I would try to, let's say, suggest that the author redo the simulation with a different technique. Just because Powell, it's okay in the first stages of the evolution, but it's not so reliable. So I would go with something more sophisticated, honestly. So divergence cleaning is not much more difficult than Powell, actually, and it works much better. Okay.
Well, thank you.
But don't tell your student not to work too much. You can write to me. Also, because I think that the relativistic formulation of Powell has never been totally checked for the relativistic MHD module. But okay, if he has a problem, he can write to me. I'll try to help him out. But the divergence screening it requires only one more scalar to be added, and that is handled by the code almost all the time, except in the case where you use user-defined boundary conditions. Okay.
Yeah, he's listening. He's actually organizing this. So
yes.